All right, we're back. We're still in section 5.4, so we're still working with that derivative of e and e to those exponents. Today, though, we're going to focus in on increasing and decreasing intervals, concavity, which all lead to curve sketching. I'm not going to sketch a curve for you, but you should be able to once you find your increasing and decreasing intervals, your concavity, your points of inflection, all that wonderful good jazz and good stuff. So, let's go ahead then and talk about increasing and decreasing intervals. Where do increasing and decreasing intervals occur? Well, they must come from the first derivative. So we're going to go ahead and find our first derivative here for x squared e to the negative x. First derivative, we have a product rule. We have x squared. Derivative e to the negative x is negative e to the negative x. So then we're going to add e to the negative x times the derivative of x squared, which is 2x. I'm going to go ahead and clean this up a little bit, factoring out an e to the negative x and an x. And that's going to leave us with an x out of the first part, minus, since I took out that negative, that's going to make the second part negative since they're all being positive there, minus a 2. And we'll go ahead and set that equal to 0 to find my critical points. So here I have three things being multiplied together to give me 0. I have negative e to the negative x, I'm going to set equal to 0. I have x equal to 0, and I have x minus 2 equal to 0. If I think about negative e to the negative x equaling 0, that can't happen. E to an exponent will never equal 0. If you think about the graph of e to the negative x, or e to the x, well, e to the x, recall, looks something like this. E to the negative x, if I get a different colored marker here, maybe it'll show up. E to the negative x will look something like this. And if I take the negative of it, it's just going to flip it or reflect it across that x-axis. So I will never equal 0. I can get close to it. The limit is 0 as we get closer and closer and closer to infinity, as x gets closer to infinity and negative infinity, but, depending on which function it was there, I guess, but will never equal 0. So whenever we have e to an exponent equal to 0, we know that that's not possible. Here I get x equals 0, and I have x equals 2. So, with my function, remember we're going to go ahead and find our intervals. You thought we were done with these, didn't you? Think again. Ha 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 ha. So we have infinity to 0, our first critical point, and then we go 0 to our next critical point, which is 2, and then 2 to infinity. We're going to come up with some test values. We're going to find a number between negative infinity and 0. I'm going to do negative 1, 0 and 2, which I'm going to use 1, and then 2 to infinity, I'm going to use 3. And I'm going to look for the sign of f prime of x. So again, here's my f prime in this part here. I'm going to plug in my negative 1. We already have a negative out here, so we can put that negative there, I suppose. E to an exponent, that will always be positive. We'll never be able to make that negative. This out here will make it negative, but we already have that negative there. So e to the negative x, that's going to give us a positive. X, well, if I plug in negative 1, I still get a negative 1. And then negative 1 minus 2, that's going to be a negative as well. So I get a negative times a positive times a negative times a negative, which is a negative. So it tells us we're decreasing. If I plug in 1, again, I have that negative out there. So I have a negative. E to the negative x, that's always going to be a positive. If I plug in 1, that's going to be a positive. And then 1 minus 2, that's a negative. So I get a negative times a positive times a positive times a negative, which is positive. That tells me the function is increasing. And if I plug in 3, I'm going to have a negative times a positive. Again, times a positive. The x is going to be positive when we plug in 3. And then 3 minus 2 gives me another positive. So I have a negative times a positive times a positive times a positive, which is a negative. So I'm decreasing. So I'm decreasing on the intervals negative infinity to 0, union 2 to infinity. and I'm increasing on the interval from 0 to 2. Now again, we could find our relative extrema, our relative max, and our relative min as well. Because we know if we go from a negative to a positive, if we go from a negative, a decreasing, to an increasing, what's going to happen there? We're going to have, you guessed it, a relative minimum. So we have a relative minimum here. We could plug in that value when x equals 0. And from increasing to decreasing, we have a relative max. Again, increasing to decreasing, that's going to have a high point relative max at x equals 2. Again, you could plug these x's in to the original to find the actual point if it were to ask you. Little bonus there for you. Next thing we're talking about is the points of inflection and discussing the concavities. So remember, points of inflection come from, you guessed it, the second derivative. So the first thing we do is find the first derivative. The first derivative of 4e to the negative x squared. We can come off to the side and let g of x equal our exponent. If you need to do this, please, by all means, do it. We've done it for several videos here now. You may continue to need to do that, which is quite all right with me. So derivative of negative x squared is negative 2x. So we take that derivative and we'll multiply it to the 4. And that's going to give us a negative 8x. And then the exponent of e will never change. And I can go into the second derivative. Here I have a product rule. Product rule. I have negative 8x and then derivative of e to negative x squared. Again, I take the derivative of the exponent, which is negative 2x, and then e to the negative x squared. To that, we're going to add e to the negative x squared times the derivative of my first, which is negative 8. I'm going to go ahead and clean this up. I can pull out a negative 8 and an e to the negative x squared. So I get negative 8 e to the negative x squared times what? Well, I have an x squared and I have a 2, so I have a 2x squared plus 1. We're going to go ahead and set, oh, that's a negative 2x squared, isn't it? Whew, almost lost the negative. We're going to set that equal to 0. So, what do we have? Well, again, we're going to set each part equal to 0, so I have negative 8 equals 0. That doesn't make sense, so we get rid of that. We have e to negative x squared equals 0. Again, remember, if we have e to an exponent, that will never equal 0, so we get rid of that. So then we get negative 2x squared plus 1 equals 0. Go ahead and solve for x. I'm going to subtract 1, divide by 2. So x squared equals 1/2. Take the square root of both sides, so x equals plus or minus the square root of 1/2. If you want to rationalize that, you can. Radical 2 over 2. It's quite up to you if you want to do that or not. So for our concavity and points of inflection, so we're going to go ahead and do our intervals, our interval charts. We're going to go from negative infinity to our first critical point, which is negative radical 2 over 2. We have negative radical 2 over 2 to radical 2 over 2, and radical 2 over 2 to infinity. You may need to go ahead and approximate the square root of 2 over 2. You can do that in your calculator, and I'm okay with that if you don't remember it from trig, although some of you hopefully remember that from trig. So we take the square root of 2 divided by 2, 0.707. Yeah, remember that? Square root of 2 over 2. Sine or cosine of 45 degrees or pi over 4. Yeah, ding, 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 ding. So we're going to test. So we have a number between negative infinity and negative 0.707. So negative 1 would work. Between negative 0.707 and 0.707, how about 0? And then 0.707 to infinity, which maybe 1 would work for us, wouldn't it? And we're looking for the sign then of the first or the second derivative sign. So we plug in negative 1. Where am I going to plug this in at? I would go right up here to figure out my sign, because that's where I have all the things being multiplied together. So if I take negative 1 and plug it in, well, negative 8 is going to stay a negative. That doesn't matter. e to any exponent is going to be positive. -1, that's going to be a positive. So I get -2 plus 1, which is going to be a negative. So that gives me a positive. If the second derivative is positive, it's concave up on that interval. If I plug in 0, again, my first two are always going to be negative and positive. It's always going to be this quantity here. It's going to determine if it's going to be negative or positive in the end. So here's 0. That's going to give me a positive, isn't it? So I got negative times a positive, which is negative or concave down. And if I plug in 1, I get a negative times a positive. And -2 plus 1 gives me another negative. So I get a positive, which is concave up again. So what can we do with that? What do we know? We know we're concave up on the intervals -infinity to -2/2 and √2/2 to infinity. We're concave down on -2/2 and √2/2. Points of inflection. So when we change concavity, we have a possible point of inflection. Remember, it's not a point of inflection until we take and plug these in and make sure we get a point. So we got to find f of -2/2 and f of √2/2 to make sure that they are actual points. So if I take √2/2 and -2/2 and plug it in, I'm going to put it up here, I guess. If I plug in √2/2, I have e to the -2/2 squared. √2/2 squared, well, that gives me 2/4, which is 1/2. So I have 4e to the -1/2. And of course, that's going to be a point, isn't it? So I get 4e to the -1/2. Now if I plug in radical 2/2, well, what's going to happen besides nothing? It's going to stay the same, isn't it? So I get 4e to the -1/2 as well. Oh, there we go. So I do get points. I get plus or minus radical 2/2 and 4e to the -1/2. We can make that a positive by putting it in our denominator, or 4/e to the 1/2. And that gives us examples of points of inflection. Last but not least, absolute extrema. Extrema, recall, come from the first derivative. First derivative, we have product rule. So we have x derivative of e to the -x squared gives us -2x e to the -x squared. So we're going to add e to the -x squared times the derivative of x, which is 1. We can go ahead and pull out an e to the -x squared. And we're left with a -2x squared plus 1. That looks very familiar to me, doesn't it? Doesn't it to you? So we're going to set each part equal to 0. So e to the -x squared equals 0. That doesn't give us anything. Remember, an exponential can never equal 0. And -2x squared plus 1 set equal to 0. Subtract the 1, divide by the -2x squared equals 1/2. Take the square root of both sides. So x equals plus or minus the square root of 1/2, or radical 2/2. We just saw that, didn't we? Yes, we did. So we need to then, to find the absolute extrema on an interval from 0 to 2, remember we test the endpoints. So we find f of 0 and f of 2. But we also test any values in between, any critical values in between that we find from that first derivative. So we just have the radical 2/2. The negative does not work because we're only looking for positive 0, from 0 to positive 2. So what I would suggest that you do is go ahead and throw this into our calculator. I'm going to go to my y equals, and I'm going to type in that function, x e to the -x squared. And I'm going to go ahead and do my table, because I have it set up for a ask table, so you can go ahead and type in whatever number you want. I'm going to type in 0, and I get 0. I type in 2, oh, there it is, 0.0366, and radical 2 over 2. So I can actually type that in, divided by, or radical 2, and my parentheses, divided by 2, and that gives me, remember my 0.707 from the previous example, and that gives me a 0.4289. So my absolute max is going to be my highest possible value there, which is going to be the 0.42. So it's going to be at radical 2 over 2, 0.428. So I can go ahead and, if you want, give the point. 0.429 there. And my absolute min is going to occur at the smallest number, which is going to be 0. So I get the 0.00. Again, remember with the absolute extrema, we can give the point, we can give where it is at, the x values, or what it is, which is the y values. So there you go. So there's examples of points of inflection, increasing, decreasing intervals, and absolute extrema. Good luck, enjoy, and if you have questions, let me know.